All right, so in this section, we're going to cover parametrized curves or parametric curves. Now, so far, I guess in algebra and even in this class here, we've gone with the kind of formulation of our Cartesian coordinate. We have x and t, excuse me, x and y, and we had our independent variable be x, right? And our dependent variable will be y. Right, so most of our, at least functions we can think of, right, some kind of input, and then we have functions like here, some curve, right, where it passed the horizontal line test, right? And in terms of applications, if we describe like one-dimensional motion, right, this model works very well, right, where we can take the horizontal x to be maybe the passage of time here, right, and then this vertical axis y, some kind of displacement, right? So as kind of x progressed, we can chart kind of the displacement of an object relative to the origin, right? Where y might be the distance from the origin, right? Sometimes I get away from it, then I get closer to it, right? And that's useful if we have just kind of one-dimensional motion across some kind of straight line path. But what if instead I didn't have one-dimensional motion, but two-dimensional motion, right? A plane, right? And I had some object that I want to be able to orient some kind of path, right? Like maybe it's moving along this path. I want to find a way to characterize this right now. Very much not a function in the xy that we're used to kind of seeing here. So in order to represent some behavior like this, what would be helpful is we introduce some kind of parameter, right? Where if we think of this point here, the the particle or object moves across that point at a certain time t, right? So we can interpret it as like our parameter being time, and then now I'm looking at it not in a straight line distance, but distance on a plane, right? Movement in the x and the y direction, in both directions. All right, so from there, I can classify this point as being some point, some parameter, right? Now, it doesn't have to be that complicated a movement. It could also be useful to, even if it's in a circular path, right? A parameter will help us to put some kind of orientation across it, right? Is it moving in this direction, counterclockwise? Or is the path moving in a clockwise direction? Okay, so while those circles may be the same, right, the orientation is different. And parametrization of this is going to, parametric curves will help us to describe both of those behaviors. Right? So the formulation that we want to do what's called parametrize by a parameter that we're going to call t. The most intuitive way to think of this as the xy just being some two-dimensional plane, right, where you're going to chart some kind of path according to some time t, right? As t changes, it moves not just in one dimension, but along the x and the y, right? So our curve that we're going to chart, however complicated or not complicated at all, it's going to have some kind of orientation, right? And then each point will be defined by some function of t. Y will be a function of t, and x will be a function of t. All right, now here's we'll start with a very basic example of how we would do this. All right, so here if we have x, let's say that we had the curve. So for this example, I want to parametrize the curve y equals to the square root of x minus 1. Okay. Now, the most straightforward way, or just a very easy way, now, there are different parametrizations to this. I'll just go into one of them just to get an idea of, how to do this, right, in later videos, we'll look at some more interesting examples here. But let's say that we had the graph of y is equal to x minus 1. It's a square root graph. Right? General shape looks like this. All right, now a very simple parametrization would be to, when it looks like this, some kind of function, just let x of t be equal to t. Right? That's always a good straightforward approach, especially if it's like this in function notation where y is equal to some values of x. Let x of t be t, and then y of t is going to be substituting in there t minus 1. Now, similar to my Cartesian equation, we do have a domain restriction, right? Here, x must be greater than 1. Since x is t here, t must also be greater than or equal to 1. Okay, and now I can set up graphing. Well, I can start by just inputting really a bunch of values here, right? So now what is different here is that our just plotting points here. All right, so I'll start with 1, 2, 3, 4, 5. Okay, so here the x, not much, it's just the same value for t, right? X of t, well, that's just t, so this is still 1, 2, 3, 4, 5. All right, and then here, y of t, 1 minus 1 is 0, square root of 0. And then when I plug in 2, 2 minus 1 is 1, square root of 1 is 1. And then when we get 3, we get root 2. And when we get 4, we get 4 minus, root 2, 3. And then 5 root 4, but that's just 2. Okay, yes. Keep the same kind of notation here, right? So here, in terms of the graph, as you see, the parametrization doesn't change the graph. But now what it does do, it does add a direction, right? So now it has, we see the direction here is very much going in this direction here. Okay. All right. And now it's in parametrized form with it going in that particular direction there. Okay. All right. And that is just a very basic example how we parametrize a curve.